Okay, so good morning. So to, Today I'm going to really discuss the cases where we have some input from the microscopic theories. So I mean that I want to consider the cases where we have some hydrodynamic solutions or hydrodynamic models, but they are derived usually from the microscopic theory. So then, if we have a chance to get solutions of the microscopic theory, then we can also compare the solutions of hydrodynamics, which is the approximations to the microscopic theory, and see whether the hydrodynamics really is an effective theory, whether it really describes well some observables. And such things have been done, but they are to a large extent restricted to one-dimensional expansion. So, and actually one-dimensional expansion, which is Bose invariant. So before I go to the comparisons, I will make a step back, and I will discuss one-dimensional models, which are quite famous. So I think it's worth to talk about them, and they will set up some stage for the discussion of one-dimensional expansion, but they are perfectly good models actually. So, but what's the physics motivation? So this is maybe the first plot with the data, just to give you some message. This plot shows the distribution of the net proton number in heavy ion collisions for different energies. This picture was done by the Brahms collaboration already 16 years ago. No, but the data didn't change. And I think it's a very beautiful plot and shows something unexpected, in fact. The green points are from low energies. So these are data collected AGS, and they show that proton number density in rapidity is just peaked at the center. So it's more or less like kind of Gaussian curve. So it shows kind of stopping. We call this phenomenon stopping. So if the two nuclei collide, they form the dense system, which is more or less at rest, and the baryon density is quite large. But then if you go to higher energies, if you go, for instance, to SPS energies, the square root of 17 GeV. So this was the largest energy, I think, started at CERN before the LHC started operation. So then you have the violet curve. And then you see quite interesting things. Simply, there is a dip at the middle. So it shows that somehow the two nuclei become transparent to each other. At very low energies, we have kind of stopping. Then if we go to larger energy, there are two peaks with a dip inside. So it means somehow nuclei go through each other. So the matter which is produced at the center, this is called the central region, the region where rapidity is close to zero, has lower baryon density at the edges. And now if you go to the top Greek energies, then the baryon density really goes almost to zero at the center. And that is practically zero. The baryon number is of course conserved, so it's taken away by the colliding nuclei, but they move with, or the remnants of nuclei move with very large rapidities, so they are actually even not measured. This is maybe not exactly true. There are some attempts to measure the distribution of baryon number in the, some detectors which are really able to measure the particles that are produced closely to the beam. But, there is no here that describes, protons which have rapidity of the beam at RIC. So our picture is that at lower energies, there is kind of stopping. that the two nuclei merge, and then there is explosion. But when we go to larger energies, then the baryon density in the center is practically zero. So then there are kind of two regimes. And there are two famous models, perfect fluid models. One is due to Landau, formulated in 1950, so very, very old. And the second is due to Bjorken from 1983. And somehow they are, I would say, suited to describe these two phenomena, two different regimes. So, so the Bjorken model, I will start with the newer model, Bjorken model. The Bjorken model really kind of shaped our thinking, and he, introduced hydrodynamics into the field of relativistic heavy ion collisions. There was the model by Landau, which was older, but model assumed the stopping. So actually, it was not appropriate for higher energies. So actually, Bjorken introduced this idea of Bose invariant flow, and the feature which is typical for Bose invariant is that the rapidity distribution of particles is constant. Again, somehow there is interesting, because if you look at the baryon number density, then you see that it decreases to zero at mid rapidity. But if you look at the production of pions, it is more or less always Gaussian. But the width increases with energy for the bulk production. So you may say that at very large energies, at the central rapidity region, so the region where rapidity of particles is zero. So these are particles which are produced at the right angle to the beam. Then you have kind of onset of boost invariance. And if the system is invariant, then the situation simplifies. We know that whenever you have kind of symmetry in physics, then the system is simpler to analyze. We have fewer equations and easier to solve it. Actually, Bjorken is a great physicist. He did many other things. Many people think that he deserves the Nobel Prize. He's the only one guy from those who constructed standard model who didn't get the Nobel Prize. Actually, his hydro model was really very convincing, and people started using his ideas. But I must say that there were some hydrodynamic models which were of the similar type, written before Bjorken. One was by, I think, Rudolf Hua, physicist from the Chinese physicist, the American Chinese physicist from Eugene, Oregon, US. There was also the hydro model by Sinyukov and Zinoviev, I guess, or Sinyukov and Lorenstein, where they also used the Bose invariance. So how this works somehow? Essentially, in the Bjorken model, the evolution is kind of one-dimensional. So this is still a good approximation for the early stages of heavy ion collision at very large energies when we look at the central region. And then, we have some, production of particles, and at a very short time, it makes sense to talk about production of hard particles, because due to uncertainty relation, we can really somehow think that such particles are produced, particles which have really very large momentum at short times. Later, there is already a system of quarks and gluons produced, which is equilibrium, out of local equilibrium. So this kind of light red region is a place where dissipative hydrodynamics may work well. Then after 2 or 3 Fermis, we actually are very close to equilibrium, local equilibrium, and then this perfect fluid hydrodynamics may work as a good kind of tool for description of expansion of matter. Eventually, you have phase transition to the hadron gas, and the hadron gas interacts more or less, depending on some our attitude, and eventually everything freezes out. And hadrons move freely to the detector. So we have this kind of one-dimensional picture of expansion, and what is important in the Bjorken model or in this type of Bose-invariant models, that the parts of the system that move away from the center, they decouple later. So there is this dilation time effect which is built in, that the part fluid elements that move, for instance, they move with some velocity. So on the space-time diagram, they move like this, for instance, or in the opposite direction. So they go through all those phases that I mentioned, but later, it's like muon the decay. Usually, with the decay time, I think there's something like 0.5 microseconds, but because they move very fast, they can reach Earth from the production point here. This typical time dilation effect, which is included in this type of the phase diagram, and the Bjorken model sort of automatically includes this effect of time dilation. So the system which is produced at rest, then it evolves, and it goes through all, states or phases in its evolution. But the system which moves goes again through all those phases, but at later laboratory times. So the evolution is governed by so-called proper time. Some people call it longitudinal proper time. So this is the square root of time coordinate, which is the vertical axis here, minus the beam coordinate z, which is horizontal line here. So everything is governed by the proper time instead of the laboratory ordinary time t. And then I have to tell something about the symmetries, because if I mention that the evolution is governed by the proper time, then I think it's easy to think that if we have some scalar function like the temperature, energy density, they should be really functions of tau, not of t. But we have also the flow for vector, which is not a scalar function, and then one has to find some forms of the flow which are Bose invariant. So I have just spoken about the symmetry. I can talk about the rotational symmetry because we all understand what it is. So the three figures upstairs, they show simply flow, which is rotationally symmetric. And somehow what it actually means, it means that if I take some vector and I make a rotation, so two things happen. First, if you make a rotation of a vector, the coordinates of the vector change, but also, it's moved to a different place, which also rotated. So we have new vector in a new place, and if there is symmetry, new vector in the new place somehow agrees with the old vector in the new place. So then we have the symmetry. If flow is not symmetric, then if we move some vector to the new place, then it doesn't agree with the old vector which was here. So the flow is not symmetric. So you can actually solve general problem of the flow which is Bose invariant, and this form is given here. This is equation number 60 here. So u mu, which is 1 over tau, then the time coordinates t and the longitudinal coordinate is z. It gives flow which has this property that if we make the boost to the new place, it agrees with the old flow in old place. So this was kind of invention of Bjorken, also of Hua, of Gorenstein, that they introduced such a flow, Bose invariant. Actually, this is not the general four vector which is Bose invariant, because there are other forms. This is you know, the 4-vector which is Boost invariant has no transverse components, and you know the longitudinal component is 0 at the origin of the system. Yeah. So to summarize, I think all scalar functions in hydrodynamics of Bjorken should be functions of the proper time. So energy density, pressure, temperature, they should be functions of the longitudinal proper time. But the proof has this form, and then you can also calculate the expansion tensor or scalar. I called it theta. So the mu is 1 over proper time. So it's, you know, all mass becomes very, very simple in this case. Also, the initial condition should be put on the hyperbola of the constant proper time. And then, okay, there are further simplifications in the Bjorken model. You probably know what is the rapidity of a particle. It's just the measure of the longitudinal velocity. So the hyperbolic tangent of y is longitudinal velocity, or rapidity is just arc tangent of hyperbolic of longitudinal v. But in the Bjorken model, I think we assume that all fluid elements really move with the velocity which is c over t, which is somehow given by equation 60. We identify the longitudinal velocity from this expression that is z over t. So somehow rapidity of the fluid element is given by, you know, its position. Everything is correlated. So the time coordinate and the longitudinal coordinate can be expressed by the proper time, the rapidity of the fluid element, which is nothing else by this quantity. Yes. And now, what is very simple is the solution for the entropy, which is conserved. In the perfect fluid approach, the entropy is conserved, and in this very simple variant expansion, the conservation of the entropy gives you a simple differential equation. The convective derivative of the entropy density is just the derivative of S with respect to the proper time. S is a function of the proper time, and the second term in this continuity equation gives you S times the derivative divergence of flow, which is 1 over tau. So you have a simple differential equation. The derivative of S is simply minus S over tau, and the solution is of this form. Simply S scales with the inverse of the proper time. So if we know S at some initial time, then we know, you know, the entropy density at later time is 1 over tau. So it's very cool. If we have energy density, so equation 66 is just the Euler equation. It's also very easy to be solved if we have equation of state assumed in some form. In this case, usually one assumes the ideal equation of state for massless particles. So P is 1/3 of the energy density. So then you can also find energy density as a function of time. Generally, the square is denoted here by lambda. Okay, so but there is some relation between, of course, energy density and entropy density if the equation of state is known. And now the most important thing, which is actually used in many experimental work, and many people say that, okay, Bjorken repeated something what was done by Rudy Hua before, but what was not in the previous papers, what was present in Bjorken's paper was estimate of the initial entropy density or initial energy density in the system. And very commonly, by all the experiments. This is one of the simple estimates what an initial energy of plasma could be. So the idea is again related to the conservation of the entropy. Introduce the volume of the fluid element. So this is just D3x. Now the transverse coordinates we kept untouched. We just say this is D2x curve, so like dx, dy, but y being the transverse coordinate. But the longitudinal, the longitudinal distance or the interval, the longitudinal distance can be written as the proper time times the difference of the rapidity. So if we want to calculate, the entropy in some volume, we have to integrate over the transverse coordinates and over the rapidity. And then, so ds is s of tau times d3x. Then we do the integral. But because in this measure we have the proper time dy, then we can put in front of the integral the product of tau times s. But this quantity is conserved, because if we looked into the solution of the entropy equation, the product of s and tau doesn't change with time. So actually, the most important result was that entropy of the system per unit rapidity doesn't change in time. It's constant. Okay. So the derivative is zero, but it means that the entropy per unit rapidity is constant. So now there are further kind of simplifying arguments that entropy is related to the particle density. The paper by Bjorken, he had idea about the pions. Of course, there's the phase transition, but generally for bosons, there is a relation between entropy density and particle density, which is given by the zeta Riemann function, and about 3.6. So if we have the multiplicity measured, we can have some rough idea about the entropy of the particles. So so the idea is to measure multiplicity of the particles which are produced and refer it to the initial entropy. So ds over dy is not changing time. So we can calculate the initial entropy density dividing the rapidity density of the entropy by the proper time and the transverse area of the system. And the transverse area of the system is just obtained from pure geometric argument. This is the area of the projection of the sphere, which represents the nucleus. So we can easily calculate it and determine it by the atomic number and the nuclear saturation density. So we have some estimate of the initial entropy density, the initial time. So the equation 71, so this equation gives this relation with dn over dy at rapidity equals 0. We have, a factor which translates multiplicity to entropy density for bosons. And what is really unknown here is the initial proper time. But people usually say that, okay, perfect hydro may start at 1 Fermi, maybe 2 Fermis. So there is some uncertainty, but up to a factor maybe of 2. So then one can make the estimate of the initial entropy density. But if we know the equation of state, we can relate it to the energy density. And to make all those arguments short, I can only tell you that all those arguments tell us that the energy density at the time of about 1 Fermi is really a few GeV per Fermi cubed. So it's much larger quantity that characterizes just nuclear matter, where the energy density is a fraction of 1 GeV per Fermi cubed. So this kind of argument, which is repeated by experimentalists, also very, I would say, convinced that that simple estimate of the energy density suggests that we have kind of new state of matter, because this matter with such large energy density cannot, be the matter which consists of nucleons, because nucleons overlap. If you have such large energy density, it's not written here, but these are, something like 5 GeV per Fermi cube. So this energy density cannot be realized by nucleons. You have to pack. We would have to pack them so dense that they overlap. So it doesn't make any sense to talk about separate hadrons. Okay, so this picture, which is valued at very large energy, is very, very convincing. I think there are simple estimates that directly indicate that energy density of the produced system at early times is really very, very high, and this is not this simple system of hadrons, in particular of nucleons. Well, so this is the Bjorken model, one-dimensional Booth invariant model. It's useful for practical applications, for doing experimental estimates, but it's also convenient for doing simple, calculations involving hydro. And also the opposite picture, which was old, and formulated in the 1950s, and still people come back to this approach, is the Landau model. So this is also quite interesting. It would correspond to this regime of full stop. Landau assumed that actually he studied not nuclear collisions, he studied proton-proton collisions in 1950s. So if people say that only now people use hydro to describe proton-proton collisions, they make error, because actually Landau was the first, I think, who was brave enough to use hydrodynamics to describe proton-proton collisions in 1950s. And he actually realized that hydrodynamic equations can be written in some nice form. This was again done for zero baryon chemical potential and for massless particles. And then the hydrodynamic equations have very simple form. Simply the time derivative of the temperature times the longitudinal component of the flow is equal to the longitudinal z component or x3 component of the temperature times the time component of flow. So it's kind of rotation at zero of the field, which is obtained by multiplying temperature by the flow. So the immediate solution is that T times U0 should be the kind of derivative of some potential phi, derivative with respect to time, and TU3 should be the space derivative of the same potential. I call it phi L to L stands for lambda here. But then what turns out, and this was explained in the paper by Landau and Kalatnikov, and I think Kalatnikov did probably the math, that you can go from phi to a new potential, which is called chi by Landau and collaborators, and you do the Legendre transformation. And now you calculate the derivative of chi, so then you see that chi depends on the temperature and also on rapidity, which is now called theta, because this is the notation from Landau. Yes, so sorry for this kind of change notation. But they come back to the entropy conservation equation, and then they can prove that using the new potential, the chi potential, one gets one differential equation which is of the higher order. So, okay, we can understand that we start with two differential equations, like equations here, 38, and we can replace them by one equation with higher order. But truth really, this equation is the telegraphist equation. So I think they make all those kind of transformations because they knew how to solve this equation I mean equation 44, analytically, and you can solve it. I don't go into details. You can explain that. Okay, you can express the solution in terms of Bessel functions. I only tell you picture is somehow behind the Landau model. In Bjork's model, nuclei go through each other. You have some color strings that produce the Bose invariant, baryon-free matter, which is Bose invariant. In the Landau model, the picture is opposite. Simply, two nuclei are stopped, a huge stopping, and the matter is compressed, a kind of cylinder which has the length which is obtained by division of the radius of the nucleus by the gamma factor. So the collision, really a collision of Lorentz contracted nuclei, they stop. So you have a very dense system because the length is really the size of the nuclei, which is Lorentz contracted. So we have some system which is at rest at the beginning. So there is no motion, longitudinal motion like in the Bjork model. And at the beginning, the system is at rest. But there is huge gradient. Actually, the gradient is infinite because you have some hot matter inside. One assumes some temperature here, so one assumes some thermalization of this matter which was stopped. But there is zero pressure outside. So actually, we have the system, hot system, with a step-like gradient which expands into vacuum. So actually, such solution is known for matter expanding into vacuum, and this is known in non-relativistic physics. It was constructed by Riemann, and actually the relativistic solution is very, very similar. So the edge, the system really expands into vacuum. This expansion is described by the Riemann solution. So the Riemann solution, for matter outside of the initial block somehow is describes the expansion with the speed of light. So this is described by those solid rows. But there is the refraction wave entering the system, and this refraction wave enters with the sound velocity. And then when the sound wave hits the center of the system, it bounces back. And then the solution is really quite complicated because there is, this refraction wave which was bounced back, and there is a refraction wave which enters the system, and there is still, this expansion to the vacuum. So everything can be really solved analytically, and this was done by Kalapnikov, and the model is analytic, and so people like it. And also at lower energies, I think it makes sense. But what it gives you as a result, it gives you, Gaussian shape of the temperature, or generally speaking, of the multiplicity of the particles in rapidity. So this was the great advantage because, and the success of this model, and people started using it. Of course, Landau did it, so the model was really developed by other people, and people followed his ideas. But if you do really all those calculations, which can be done analytically, then you see that the multiplicity distribution of particles is a Gaussian, and this is experimentally observed fact that such distributions are Gaussians. So the model had some piece of truth inside, and became quite popular. So now, okay. So I reviewed sort of two complementary, very famous hydrodynamic models, which are based on two different concepts of full stopping and full transparency. Now, if we want to go and include dissipation, then we see that actually the dissipative effects are very large. So this is the slide which I show probably for the third or fourth times, because I want to just emphasize that there are these corrections to the energy momentum tensor which are due to viscosity. And actually one can, for one-dimensional expansion, which is described by perfect fluid models, you can make some estimate how pressure in the longitudinal direction is different from the transverse pressure, because the shear tensor somehow induces difference between the longitudinal and transverse component of pressure. Of course, we are used to think of pressure as it's always isotropic, but so what I mean by different components of pressure, I mean here different components of the energy momentum tensor. So this is 4x4 kind of matrix, but there is a 3x3 submatrix, which is the pressure tensor or shear tensor. And then you can look at the diagonal terms and define pressure components in different directions. For perfect fluid, they are all the same. The system is isotropic. But if we have effects due to shear viscosity, then the pressure become different. And actually, if we assume Bjorken expansion, and then we can calculate using the Navier-Stokes expression the ratio of the longitudinal pressure to the transverse pressure, and then the effects of the longitudinal expansion of longitudinal gradients make the longitudinal pressure lower compared to the transverse pressure. And this difference is induced by the ratio, exactly the ratio of the shear viscosity to the entropy density. So this is this famous measure of the viscous effects. And, ADS, CFT, or quantum mechanical calculations gives you some hints that this value is, this ratio is 1/4 pi. If you use it for RIC, like initial conditions with the initial temperature of 400 MeV, and you want to start your hydro evolution at 0.5 Fermi over C, you see that the longitudinal pressure is just 1/2 of the transverse pressure. So it's really a big difference. The system is not isotropic. For the LHC, the effect is even stronger. Temperature is larger, but usually we start hydro earlier, and then P over PT from Navier-Stokes with the Bjorken geometry is 0.35. So this shows somehow that we have to abandon perfect fluid description of early stages. We have to go to dissipative hydrodynamics, but of course it's difficult to also to admit this quantity, because you see these are quite substantial difference. So this system is really away from local equilibrium at early stages. So I think the next part of the talk, I would like to present two comparisons with the kinetic theory and with the ADS CFT results to argue how we can somehow, what we can learn somehow, what we can learn about, this behavior of hydro, and how hydro can really well describe such, anisotropies. So I think I will probably stop now and maybe take some questions from you, if you have. I think it's maybe again good time to make really a break. But first questions. So are there any questions? Okay, so let's make a break of 10 minutes, and we shall continue with comparisons of hydro with the kinetic theory. Okay? So thank you. Thanks for late. Yeah. Okay. So I'm going now to discuss comparisons with the kinetic theory, comparisons of hydrodynamic models which are, constructed with the help of the kinetic theory. So effective theories with the microscopic original theories, So it is possible if we really have, sort of exact solutions of the microscopic theory, and this is possible if we have really very simple systems. So what we do, we can start with the kinetic theory. So with the Boltzmann equation and with our favorite relaxation time approximation. I already told you that Amaresh, Jaiswald worked out the full hydrodynamic formalism of dissipative, actually, hydrodynamics. And this formalism is based on a very specific form of the collision term, which is here in red. Yeah, so this form tells us that actually collisions bring the distribution functions to the local equilibrium function. So there is a change f, which is due to the difference between actual distribution function f and the equilibrium one. And there is some special characteristic scale for, for this process, which is given by this relaxation time. But now what we can do, actually, we can find exact solution of this problem if we have one-dimensional expansion a la Bjorken. So just to mention one thing, so equilibrium distribution function we take here in the classical limit, in Boltzmann statistics. So the equilibrium function is just exponential here. Exponential of minus p mu times u mu. U mu is the flow, hydrodynamic flow vector. But we know that for Bose invariant systems, the flow has very specific form. So we can use it, actually. And we can also solve a little bit more general problem. I mean, which variables are really independent as the arguments of the distribution function. The distribution function really depends on the time coordinates, space coordinates, and free momentum if the particles are on the mass shell. Now, f, which is the phase-space distribution function, turns out to be actually a scalar function. The distribution of particles in the momentum is not a scalar function, but one can check that the phase-space density is the Lorentz scalar. So for Bose invariant one-dimensional expansion, the distribution function may depend on the proper time, and in addition of a special combination of the momentum and space-time coordinates, which are called W here. So this is actually the variable which was introduced by my Polish supervisor some time ago, by Białas and Czyż, and W is time times longitudinal momentum of the particles minus Z component times the energy of the particle. So we can think that W is like the longitudinal momentum, because for the Bose invariant system, everything that happens at the plane Z equal to 0, so at mid-rapidity exactly, happens, in copies for finite values of Z. So if we, set Z equal to 0, then we see that W is more or less longitudinal momentum. I said more or less because it's multiplied by the time. And there's another variable which is useful, but it depends on W. V is like the energy for Z equals to 0. So the distribution function for such transverse Bose invariant, for longitudinal Bose invariant expansion, and for the system which are uniform in the transverse space, such functions depend really on proper time and W. And now it turns out that the original Boltzmann equation in the relaxation time approximation simplified quite simple equation where we have only the derivative of the distribution function to the proper time, and on the right hand side we have the difference of the actual distribution function f and the equilibrium function. The difference is divided by the relaxation time. Now the equilibrium function has this form. We want to use the variable w, which is invariant. And so once again, I think w is boost invariant. If you make the boost, w will be, it not change. It is a scalar. So the equilibrium function, which is a function of tau, w, and transverse momenta, has this form. So it's nothing else like, Boltzmann distribution, but only written in terms of w. And now, actually, this approach was popularized by Gordon Bain in 1940s. There is a formal solution of this equation, which can be written in the integral form, that actually the distribution function at some time tau is given as the initial distribution f0 multiplied by some function d. And there is a kind of memory in the system. There is kind of integral over the equilibrium distribution functions over the time tau prime, and tau prime stretches from tau 0 to the actual time tau. So this is the formal solution, and d is called the damping function. It's just exponential of the integral of the inverse relaxation time. And now, so the formal solution is known. One can solve it really by making some iteration of this equation. So we can actually get f exactly. The issue is about the initial distribution. And I mentioned before the break that the system is anisotropic at the very early stages. And so we want to use as the initial distribution, the distribution which accounts for anisotropy. So this is done using Gromacka-Strickland form. Actually, this form is also the basis of anisotropic hydrodynamics, where we say that, this form is good approximation for the distribution function during the whole evolution of the system. But in this case, we use Gromacka-Strickland anisotropic distribution at initial distribution function f0. So at tau equal tau 0 at the initial time, distribution is anisotropic, and anisotropy in the momentum is defined by the parameter psi0. So psi 0 is the initial value of the anisotropy in the momentum space. And lambda 0 is kind of initial scale for the transverse momentum. So it related to effective temperature. It defines also the net density of the system together, of course, with psi 0. And then, so we can solve exactly the kinetic theory for one-dimensional expansion, which is boost invariant, and the collision term is treated in the relaxation time approximation. We can just solve it, exactly, and then we can compare the results with the results of hydrodynamic, models or hydrodynamic frameworks, which are constructed from the kinetic theory in different concepts. So there are many, plots here. 3 columns describe the energy density of the system divided by the initial energy density, the ratio of the longitudinal pressure multiplied by a factor of 3. Again, the ratio with respect to the initial energy density, and also the ratio of the transverse pressure to the initial energy density. So there are 3 columns describing different sort of observables. Now we have different values of the viscosity here. The relaxation time can be related to the viscosity. So we have different rows which describe different viscosity. So the first row describes the lower bound, where eta over s is 1 over 4 pi, and then we have 3 lower bounds and 10 lower bounds. And then the blue dashed dotted line is the result from Israel Stewart. Then we have dotted brown lines, which are DNMR. So the most sophisticated, I would say, approach to get hydro from the kinetic theory. Hydro is an effective model, and we have also anisotropic hydrodynamics. And you know what happens usually, you know, when the curves go close to each other, it means that hydrodynamic description is really very good description of underlying microscopic model. So then we can be happy really about how hydro works, and we can, and so then we can be also somehow assured that our scheme, our construction of hydrodynamic models is good, and we can use it instead of kinetic theory. Because kinetic theory is very complicated, you know, formalism, and it's difficult to use. You know? So hydro is so attractive because it's much simpler theoretical framework to describe the dynamics of the system. Okay, but what happens in the middle panels is that, you know, we see that the blue curve starts to deviate from the exact solution of the Boltzmann equation. Actually, with the growing viscosity, the deviations are really large, and even not shown here because PL becomes negative. You know, so if we have Israel Stewart, the original formulation, and we want to use it, then we see that, you know, simply it is not good description of microscopic model. Pressures become negative, and actually this was the motivation for Mike Strickland collaborators to develop anisotropic hydrodynamics, because he was running the code and he realized that, you know, the code crashed sometimes because the negative pressure is produced in Israel Stewart's theory. This happens usually at the edges of the system, but you see here this also happens due to, you know, large longitudinal gradients which are present in the Butin variant scenario. But on the other hand, you see that DNMR framework is much better. You know, it's closer to the exact solution. A-hydro works the best in this case because it never gives you no problems with the longitudinal pressure, and it's close to the exact solution. So the lesson from this is, you know, that one really has to apply the hydrodynamic frameworks which are the newest and the most complete. So for instance, DNMR approach, which is very general, or you know, anisotropic hydro. Otherwise, we can have problems. Of course, there is some kind of different opinion about this, because, you know, in this case, I started with some microscopic theory. I compare it to hydro, which is, you know, constructed in relation to the I shouldn't worry about this negative pressure, because we use hydro as an, you know, as a hydrodynamic tool. Okay, there was some break. So, you know, I may repeat some people don't worry about negative pressures which appear in hydrodynamics, because they say, okay, we use hydro, which is constructed without any reference to microscopic theory. So, you know, if it leads to negative pressure, okay, so this is the life, you know, there are some systems which have negative pressures, so maybe our hydro really describes this situation. But, okay, so I would say this is right to say so. But on the other hand, if we have, you know, theoretical framework, we want to somehow say that it's kind of approximation to microscopic theory, we clearly see that Israel Stewart fails, you know. So one has to do better, and probably one has to use DNMR or isotropic hydrodynamics. DNMR has this advantage that it's also constructed for any, I would say, collision term. And isotropic hydrodynamics is based on the relaxation time approximation always for any expansion, but for... Okay, now I have something more to say, because The previous case was, you know, the case with particles which were massless. But now we can switch to the case where we have bulk viscosity present and we have massive particles. And there are different options, you know. For instance, we have the simplest version of the terms, you know, containing beta coefficients. There's again problem. Yeah. Okay, so you know there are three versions ABC of the dynamic equations for the bulk viscosity. So depending on different, you know, formulation of hydrodynamics on your attitude, whether you want to take more or fewer terms, you know, there are more or fewer terms on the right hand side. So we have ABC model. You know, C is the simplest, A is the most complicated, and what we did, you know, some time ago, we, you know, used the hydrodynamic models and we compared with exact solutions of the, you know, kinetic theory for massive particles, again, Boost invariant, the reaction time approximation. And it was a kind of shock to see that none of hydro models describe the exact solution. So the exact solution, no, the plots here, I showed the bulk pressure, which is multiplied by the proper time. And, you know, the exact solution for some initial conditions shows that, for instance, bulk pressure increases and then decreases. The first order hydrodynamics, so Navier-Stokes theory is described by the dashed line. So after a long evolution, actually bulk pressure is really approaching the Navier-Stokes regime. So this is, I think, correct and expected. But if we use Israel-Stewart, you know, hydrodynamics in different versions, versions ABC, then we see that the behavior is completely different. You know, the true sort of bulk viscosity, bulk pressure grows, but hydrodynamic equations tell us that this decreases. Yeah. For some other different, some other initial conditions, the situation is similar somehow. Maybe not so drastic difference is seen here, but again, there are differences. And for instance, the model C seems to agree with the exact kinetic solution here. But on the other hand, for the conditions which were plotted in the left panel, this model is the worst. So actually, nothing really here, except for very long times where everything approaches Navier-Stokes regime. Okay, and what is the solution of this? The solution is that all, you know, these very well, I would say, established Stewart-like hydrodynamic approaches do not include the coupling between the bulk shear sector. So such terms were identified only by the Frankfurt group. And then if you really do full DNMR with the terms that couple, you know, this bulk sector to the shear sector, you get, I would say, agreement with the exact solution. So again, the lesson is that one has to use the newest versions of hydrodynamic models if we want to probably have a reliable hydrodynamic approach, and especially if we want to describe, you know, effects connected with bulk pressure. So, for instance, the case where we have no conformal symmetry, then the terms which were identified the last years are really important because they play important role to get the agreement between exact solutions and hydrodynamics. We always want to have hydrodynamics as an effective theory that describes the system. And in the possible range of the the parameters. Okay, so these were lessons from the comparisons between hydrodynamic and kinetic theory. There are many new developments, but I think I will have no time to go into case. This became very popular, I would say, activity to study exact solutions to the kinetic theories for different actually known expansion profile, which can be treated analytically and make comparison between kinetic theory and hydro. But another, I would say, input which is even, I think, more important and suggestive, and also more attractive from the theoretical point of view, are insights from the ADS-CFT correspondence. So it was realized, and this is one of the probably most famous results in the theoretical physics of the last, I would say, maybe 20 years, is that, or 30 years, is that, there is kind of correspondence between conformal field theory, the strong coupling, and string theory. And in the case where the coupling of the field theory is very strong, then the string theory becomes really well described by the gravity, which is weakly coupled. So there's the so-called ADS-CFT correspondence that allows us to somehow find the solutions in the strongly interacting field theory from the solutions of general theory of relativity. So this again became kind of a theoretical, very popular topic of research, that one solves, finds some solutions on the gravity side and transforms them into the solutions on the field theory side. This conformal field theory, which is, we say, dual to gravity, is actually not QCD. It's a conformal theory. We know that QCD breaks conformal symmetry. There are no quarks. The quarks are replaced by scalar fields and Weyl spinors. So this is not exactly QCD, but this theory, its correspondence allowed us to determine, or us physicists, determine the viscosity to entropy ratio, which is 1/4 pi. This value also is kind of measured in heavy ion collisions. So this suggests that quark-gluon plasma is really a strongly interacting system with the minimum value of the ratio of eta over S. And now, what was done actually by my friends from Krakow, they made many really calculations, for different initial conditions, and they also studied, the difference between the transverse and longitudinal pressure for such systems, which are very strongly interacting. So ratio is, R is the ratio of the difference T minus PL over sort of average equilibrium ratio. And now what they construct, they want to analyze dimensionless quantities. So first they, instead of the temperature, which is the only trivial thermodynamic quantity in this game, they consider the product of the temperature and the proper time. They call it W. W has nothing to do with my W I had in my kinetic theory. This is their notation for the product of the proper time and the temperature. And then they construct a function, which is again dimensionless, is the ratio of W with respect to the proper time, but multiplied by the time and divided by W. So this function is actually, a logarithmic derivative of W with respect to time, and it's related to this ratio. So one can start F instead of this ratio, and one can compute, how W, this function F, behaves for W, which is very, very large, So actually for for large times, W goes to infinity. So actually, W is kind of gradient expansion. Expansion in powers of 1 over W is the gradient expansion, and you can do it for such models analytically and find, the first terms of the series which like this. Actually, these terms can be also, related to viscosity. So this type of the calculation gives you, famous results for the ratio of eta to the entropy deficit. This is 1 over 4 pi. So this is the famous result by Koftonson and Starry Nets. But you can get somehow information about different terms. I mean, higher terms in this expansion. This expansion is nothing else like the kind of gradient expansion of this difference of pressure scaled by the original pressure. So, okay, you can determine kinetic coefficients in this game for this theory, conformal field theory, but you can also study different solutions corresponding to different initial conditions. And this was done by Heller, Janik, and Wojciech, so my Polish colleagues. And this is the famous paper, already almost 10 years old. What they show is really that, all solutions which are, describing this very strongly interacting system, they actually approach hydrodynamic regime. But what is really interesting is that if this hydrodynamic approach is achieved, still the system is highly anisotropic, because this function f of w can be kind of translated to the asymmetry of the pressure. And what they found is that there are very complicated evolutions of the system that bring the system to the hydrodynamic behavior, to the behavior which is well described by Israel Stewart, let's say. But still, PL is very different from PT. So they called this behavior a hydrodynamization. Yeah. Before I was telling you that we use perfect fluid hydrodynamics with very early starting time, and because now this framework was able to describe the data, people thought that this is kind of proof of early thermalization. But one has to switch to viscous hydrodynamics because there are deviations, the gradients are large, so one has to switch to viscous hydrodynamics. Then the improvement of the data is better, especially V2 can be described, the flow coefficient can be described better. So there is the place for viscosity, although the viscosity is around 2 over 4 pi, so it's very close to this ADS-CFT result. But the calculation which follows from ADS-CFT correspondence shows that the system really approached hydrodynamic behavior at the moment where the system is anisotropic. Yeah? So this is kind of proof. Of course, this is not general proof, but this is kind of indication that there might be some systems that, achieve this dynamic regime in a situation where we really doubt that hydro works. So this is kind of indication of unexpected efficiency of hydrodynamics, because the systems really become to behave in the hydrodynamic way. The behavior is well described by dissipative hydrodynamics, although we think that it shouldn't be applied. Hydro shouldn't be applied because gradients are large and the deviations from local equilibrium are large. So now the puzzle of early thermalization disappeared, but now we have the puzzle of early hydrodynamization. Of course, right. Right. Yes, so yes, I agree completely. I think it's, yeah, I agree somehow. So there is, I think, very striking result, you know. Of course, because this is kind of very modern physics related to string theory, so it has some, you know, impact on our minds, you know. But the question is, what, first of all, what happens? What is really reason that even in this simple model, the system becomes well described by hydrodynamics? And there were some explanations uh, um, which use the concept of attractors which are present in such systems. So actually, Spalinsky and Heller found some attractors in such systems, and there was kind of idea pushed forward that, you know, these are very complicated dynamic systems which have kind of attractors. So there are some, you know, fixed points, and the system somehow is attracted to the attractor solution, and the attractor solution eventually brings the system into this hydrodynamic behavior. But again, I can say some doubt about this. Just I can repeat what Francesco has just said, that these attractors were identified only for very simple one-dimensional Bose invariant expansion. So actually, I attended the workshop on Hydro, some new developments on Hydro last November, and there were many discussions about attractors, and I think they were not completely conclusive, you know, because there is a very little known about attractors for non-conformal cases, and also there is no, I would say, uh, any information about attractors in more dimensional systems. So this is one-dimensional expansion, which is Bose invariant, so it might be very, very specific. So you would expect maybe some, you know, attractors which are hypersurfaces in multi-dimensional, you know, space. This is not studied at all. Also, if you go with initial condition to some extremes, then, you know, the system approaches attractors or hydrodynamic behavior later, you know. So there is the question how crazy initial conditions you may take as the initial conditions, because of course if you restrict some range, initial conditions to some range, for instance, I mean, initial anisotropy is restricted to some interval, then there will be also some maximum time where we approach hydro. But if we go really to extremes, then this approach might be later. So I think there are many questions which are not answered here, but there is some hint here that hydrodynamics, dissipative hydrodynamics, may work better than I think we would expect. You know, this idea of anisotropic hydrodynamics was also, you know, triggered by some ideas that we can maybe push this, you know, applicability of hydrodynamics to the situations where usually is not applicable. I mean, to the situations where gradients are large or anisotropy of pressure is larger. So there is a general, I would say, effort on the theory side to develop hydrodynamics in this direction that we can enter the non-equilibrium, I would say, non-equilibrium, range in some reasonable way. But this, this is kind of very nice illustration, and whenever you have a model which is solvable exactly, then you can ask some questions within this model and answer this question. So this shows that there is really this kind of hydrodynamization. But the guys did more interesting things. I mean, those who studied this hydrodynamic behavior, they simply found that if you make really this expansion in terms of W, if you study such series, then these coefficients R really grow more than n factorial. So this gradient expansion is really not convergent, is an asymptotic series. And this is easily understood because, we have non-hydrodynamic modes in our hydrodynamic modern frameworks. So Israel Stewart, also ENMR, formalism, anisotropic hydro, all those hydrodynamic frameworks have non-hydrodynamic excitations. They have regulating sectors which are non-hydrodynamics, and they cannot be described by, series expansion, like in the field theory. In the field theory, you have, for instance, instantons, you have some tunneling processes, and they cannot be described by the perturbation. So the series is usually asymptotic in QED because it cannot describe all physics. So this is actually quite exciting perspective because now, our old, well-established hydrodynamics starts to look like a modern, field theory, in the sense that the series gradient expansion, which we usually think is the basis of hydrodynamics, is really not converging series, it's an asymptotic series. So its use is kind of limited. We may use first terms, but eventually we have to add non-hydrodynamic modes. We have to, complete the theory in some heuristic way, and this model works then. But hydro is more than the gradient expansion. This is also interesting development because this paper was quite famous. The paper where Heller, Yannick, Witaszczyk found that all those terms kind of diverge in the expansion, the gradient expansion. But and there was some discussion in the papers that this was seen already by Grad in 1950s, and actually even famous mathematicians like Planck was studying this problem of convergence of such series when you go from Boltzmann equation to hydrodynamics, even in the non-relativistic case. So I think this is quite general problem which reappeared again, I would say. Okay, so the gradient expansion is quite limited because usually people think, okay, hydrodynamics is expansion of gradients. We start with global equilibrium case, as I mentioned, then we go to the local equilibrium. In local equilibrium, we have gradients because temperature, for instance, depends on space-time coordinates. So we have to make some, we have to include the gradients. If there are gradients, the gradients produce some currents, some transport phenomena. So we have to include them. If you want to make better, then we have to include higher gradients. But actually, this example shows that this is not the way to do it. We have to complete the theory in such a way that we introduce somehow non-hydrodynamic modes, or in other words, we have to introduce some regularization into this theory that makes it causal stable. So we have to introduce some, phenomena which are not described as an expansion in gradient. But the gradient expansion still somehow has some value, because the gradient expansion can be now used, I think, for comparison between hydrodynamic models and some microscopic models. For instance, so this is shown here on the left-hand side. Suppose that you have energy momentum tensor for any theory. So if we are close to equilibrium, we can make some expansion. We can start with local equilibrium T mu nu, and some, gradients, some terms which are really gradients of temperature and the flow. Of course, if we add them all, we not get good description of T mu nu, but we can make this expansion. So we can do it for any theory. Of course, it's very difficult to do it, usually for really, some things like QCD, but for simple systems, you can do it. I gave you the examples. Okay, but then suppose that we have Israel-Stewart hydrodynamics, which is defined with any reference to any microscopic, theory. So we can make also gradient expansion of Israel-Stewart theory. So we make gradient expansion for underlying microscopic model or theory. We do gradient expansion for phenomenological hydrodynamic models, and then we match the gradient expansion. And this is the way to fix really the kinetic coefficients in the hydrodynamic model, yeah? So actually, this is what we do if we absorb the shear viscosity ratio 1 over 4 pi into the hydrodynamic model. We use the gradient expansion from ADS-CFT correspondence, and then we somehow absorb it to the hydrodynamic approach, which is formulated without any reference to microscopic properties. So the gradient expansion, I think, is still useful. It cannot be used, I think, to get better agreement, I would say, of the theory. I think it's like with all asymptotic series. I think we should stop at the second order. This is probably enough, maybe with the third. But somehow gradient expansion is useful to make comparison between the theories, between fundamental theories and hydrodynamic models. This is the way how we can transform, some knowledge from microscopic theories to phenomenological models. In the phenomenological models, when we use them to describe the data, we can also determine the kinetic coefficients. So then we can compare whether our kinetic coefficients agree with some fundamental theory. So this is actually useful. So this is one way. I think this is what, in my opinion, is left from all this idea of making hydrodynamics as expansion in gradient of temperature and u mu. But there's also other aspect of the gradient expansion, because, for instance, if you have a microscopic theory and we can construct hydro from the kinetic theory, so some from the microscopic theory. I said kinetic theory because at the tip of my tongue I had in mind, I had in mind the kinetic theory, which is a good example that is kind of microscopic theory. We can formulate hydrodynamic model like DNMR approach. So what we do, we usually start with a kind of gradient expansion, and then we control the terms, making, for instance, counting the Knudsen number and inverse Reynolds numbers. And then we eventually come to the hydrodynamic model with the kinetic coefficients, which are very well, I would say, very well, because they are really defined concretely, without any ambiguity. But then somehow the way also to check whether we didn't lose anything on the way, because we can make, again, gradient expansion for the kinetic theory in some case. Do the gradient expansion for the hydrodynamic model. We know the kinetic coefficients now in the hydrodynamic model, so we can check whether everything agrees somehow. So there is some tool left. There's some usage of the gradient expansion, but it is, I would say, limited. I think, in my opinion, it does make sense not to go to really higher orders than 2 in this gradient expansion. We have to complete the theory by adding the non-hydrodynamic actually mode, and that's how it works. So I guess this is the end for this lecture. What is left for tomorrow are 2 topics. So tomorrow I want to tell you about the newest development in hydro, which is done by Brazilian people, Benfica, Oronia, and some other guy who I forgot his name, Dr. Pavel Koptu. And there is this really kind of reformulation of first order Navier-Stokes hydrodynamics. And this is really kind of interesting what they did. I also want to talk about the hydrodynamics with speed. So there are 2 topics that very, I would say, new for tomorrow. But this completes my my lecturing on more traditional topics so far. Okay, so thank you, and please ask some questions. Okay, thanks. Okay. Yeah, this is over. Yeah. So I can answer some questions now, and that's it. Yeah, for today. No questions. Right. Oh yeah, so this is another story. Yeah, so this, yeah, right. So actually there is the way to make Borel summation of the series. And then if you make the Borel summation, then you can study some analytic, you know, analytic properties of the Borel transform. And for, you know, some simple theory, what was found somehow is that actually the Borel transform contains some information about non-hydrodynamic modes. So this is really kind of mathematical, uh, very intriguing situation. Ooh, the connection, the connection was lost. I heard your question, you know, so actually, you know, if you take a few terms in the gradient expansion, there are good approximation for the solution at very late times. But if you want, but if you want to have better description of earlier times, you have more terms and then you fail. Right. But you know what is written here, which was left, here maybe, this trans-series, so there is kind of um, mathematical evidence from some models that if you make Borel transform of the series, you can make, Borel resummation of the asymptotic series. And then I think there are some evidence, which is again, not general, that from the Borel transform, you can get some information about non-hydrodynamic modes. So you have asymptotic series, which is not convergent, but there is some information in the divergent series about non-hydrodynamic modes. And actually, not useful in the sense that it's not useful to add more terms. Yeah. Yeah. So maybe it's not. Yes, it was written in this. Oh, I didn't hear you well, but I mean that when theta over S is small, I think the interaction is very large, because the viscosity, yeah, because the viscosity coefficient looks okay. If you have kinetic expression for the viscosity coefficient, it goes like, for instance, the relaxation time approximation is proportional to the relaxation. Collision. The scale is very short, so the system goes to local equilibrium almost instantaneously. Yeah, so if I understood the question well, so eta small means that the interaction is very large, because in the kinetic picture, the viscosity is proportional to the collision time, this average relaxation time for the collisions. Yes? Uh, so if the relaxation time, the kinetic theory, or the mean free path goes to zero, then viscosity goes to zero. So the limit of viscosity going to zero is the limit of strongly interacting system. So, so this, and but yeah, but I didn't hear your question. So could you repeat your question? But I didn't talk about CGS at all. You know, CGS is the initial state. So CGS is before any hydro, I would say. Yeah. Of course, people say that CGS is strongly interactive, although we have weak coupling, but you have many gluons, and because of this, effectively the system is strongly interacting, but not in the sense that the coupling is large. You know. But here I didn't talk about CGC at all. You know, CGC are just for me some configurations of the initial fields, chromoelectric and chromomagnetic, that somehow decay and they produce plasma, and then everything becomes kind of hot and dense system of quarks and gluons, and then there is the place for this viscosity, but which is small. But CGC is yeah, maybe Raju was telling you that CGC has small viscosity, but this non-equilibrium phase, so actually it's even difficult to describe it, to assign some value of viscosity for this system. CGC is used to model the initial state, but then you switch to hydrodynamics, and then you use within hydrodynamics the kinetic coefficient, So CG, yeah, I did it. Yeah, so I have